7, 6, 5, 4, 2, 1. Here we are. Okay, so we start with statistical mechanics. So let us start with statistical mechanics. So what is the goal, the main idea? Statistical mechanics is essentially built on a single postulate, which is called the equal a priori probability postulate, which tells you the following. It's a very simple postulate. Suppose that you have a thermos. You know what is a thermos? The thing you put your tea in, right? And you bought a very expensive one, so it's essentially adiabatic. Energy is conserved in that thermos for a pretty long time scale. Depending on how much money you spend, the time scale is going to be longer and longer, but that's essentially the main point of buying a thermos. And now, you look at what is inside. Let's say that inside you have a liquid, or you have whatever, you have a gas. You have whatever you want inside, some substance. And now this substance is under some macroscopic conditions, right? It has some given energy, which is constant because there is no heat exchange with the external environment. There is a certain volume of that constant. There is a certain number of molecules that probably you don't know, and you never measure, but there is a certain number of molecules, hopefully, and so on and so forth. So you have certain thermodynamic variables that in principle you can measure and that are sitting inside that thermos, and you're happy with it. And now you start thinking, but look, inside the thermos I don't have water. I have a bunch of HO2 molecules that are, dangling around and sitting around with some impurities and some stuff, and they continuously move, right? And they continuously move in such a way that if I would be able to take a photograph, a picture of those molecules, right, and do like, I don't know if you've been playing with your cell phone, you have the possibility of taking pictures in a sports mode, usually, which means that you can see yourself doing this, or running, or jumping, and you can see various shots, right, at a different distance of time. So you can, in principle, do the same for your molecules inside the thermos. You would need a camera that has a pretty fast resolution, as you can imagine, because molecules are not like you or me, that we are slow, but are faster than Usain Bolt. So eventually you will not see molecules if you don't take a shot with a short enough time resolution. But imagine you can do that. So if you could do this, then in principle you could be able, by taking different pictures of your system at different instants of time, to say that the state of the molecules is continuously changing. Position, the velocities are never the same. They're continuously changing, all right? And you have a huge number of molecules whose position and velocities are fluctuating in time. And then you imagine doing the following experiment. You stay there with your cell phone and you take pictures of what's inside your thermos trillions of time. You might spend a month just taking pictures. And then you ask yourself, okay, was it a waste of time or not? Well, it turns out that then you can then ask yourself, okay, what is the probability? When you take a large number of pictures, you can pretend to look at each picture and say, okay, is there another picture in which the position of the particles and the velocities of the particles is more or less the same? Okay, and maybe you find one if you have a large enough number of repeated pictures. And then you can build an histogram and ask yourself, what is the probability of having a certain set of positions and velocities for my particles. Okay? And it turns out, if you do this experiment, hopefully nobody in this class will do it. Otherwise, I will be called by the police. But so, if you would do this experiment, it turns out that what you would find is that any, I'm going to say a big word, any microstate that is consistent with the macroscopic condition of your system is going to have equal probability to occur. What does it mean, every microstate? Every microstate means every set of positions and velocities for your molecules is going to have equal probability to be found in this set of pictures. Okay? That's it. So if you would do this experiment and would suffer through it, you would find out that this is true for a generic system, right? For, gas of molecules or water or any system. Actually, systems that satisfy this are called ergodic, but let's not dwell into all these kind of details because these are just details. Most of the systems you're interested in satisfy this property. All right, so what I said is clear, I hope. It's obvious. Let us now try to try to make it formal. Okay, write it down in mathematics. So in mathematics, when I say a microstate, what I have in mind is a gas of particles which have some generalized coordinates qi. So qi is a vector, and some generalized momenta pi. And thinking about Hamiltonian formalism, and I'm sure that all of you know everything about classical mechanics. Okay? Lagrangian formalism, Hamiltonian formalism, etc., etc., etc. So I have this set of, if I give you a set of qi and a set of pi where I runs from 1 to n, that will define for me the microstate of my system. Will tell me where each molecule is sitting and where each momentum is directed and what is the strength of that momentum. And in particular, I will have what is known as a phase space, which is our set of real numbers 6n, okay, where n is the total number of particles. And in particular, I will have a certain Hamiltonian function. So this is an h, okay, written up in a fantastic way. All right, and I will have a certain Hamiltonian function that is a function of qi and pi. And the equations of motion for my system are going to be the usual Hamilton equation. And then pi dot minus dh dq. Okay? And now let us state this. Let us make this statement that I just made, that if you take many pictures at different instants of time, you will get blah, 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 blah. So this is the following. Essentially, what I think is that you can think of it also in the following way. I mean, taking many pictures of the same system for an ergodic system is equivalent to taking many copies of the same system with the same macroscopic conditions and measuring at a single instant of time what is the position in this guy, what is the position in that guy, etc., etc. You see, it's the same thing because of ergodicity. Okay, it's equivalent. You can imagine why it is equivalent. So then you can build a probability distribution, probability density of being in a certain microstate. And the equal a priori probability postulate tells me that for a thermally isolated system, this is going to be a constant in what is known as a microcanonical shell. Sorry. I will explain what I mean in a second, and zero otherwise. So E is the energy of your system. Delta is roughly the resolution with which you measure the energy. But it's supposed to be a parameter that is small and tends to zero. It's arbitrarily small. It doesn't really matter what it is. So what you're thinking about is the following. You're thinking of having your phase space that here I'm representing as three-dimensional just because I'm not able to draw a 6n dimensional space. And you imagine having in this three-dimensional space, you can define the surface, a surface, which is the surface of points that satisfy the equation. So this guy will define a surface, right? I mean, if you have in one dimension, so when you have one Q and one P, one particle in one dimension, this stuff here will define a line, right? You can easily imagine, for example, take an harmonic oscillator, P squared plus omega squared Q squared equal to E, defines what? Defines a line that is an ellipse, right? So defines a line. If you have a 6n dimensional space, it will define a surface in one less dimension, right? But what is the volume of a surface? What is the volume of a surface? There is no volume of a surface. A surface has no volume, right? And therefore, if you don't give it a thickness, if you don't make a loacker out of this surface, you know what is a loacker? You can find it in the vending machines downstairs. It's you have never seen it? It's one of those buffers with inside the chocolate. So you know what I'm talking about, right? So we make of this hypersurface of constant energy, we make a loacker out of it. So we just take it and we give it a thickness. We put some chocolate. Why we do that? Because then, if it has a volume, we're able to normalize this probability distribution, right? Otherwise, we have all those problems of distributions. You know, what is the delta function? Is it a function or is, all this mess of... delta function is not really a function, right? Even though it's normalized. It's a distribution. It's infinite at one point and it's zero otherwise. We don't want to have those complications. So let's give it a thickness that is arbitrarily small. Okay? And this way we can just normalize this probability distribution by just saying, well, this constant is nothing but 1 divided by the volume of this of this loacker, of this whatever, which is equal to the integral of dq, the integral in phase space, restricted to the area in which E is smaller than H and smaller than E plus delta. Okay? Clear? You see that if I integrate this function here, with this normalization, I will get 1. So it's a probability distribution. Is it clear to everybody? So that's the reason why I give it a thickness. Okay? There's nothing spectacular in this.
couldn't we just take delta equal to 0 and just take the surface integral, define it that way?
Well, we will eventually do that in a second. You will see it when we define the entropy. But let me go ahead and this way. You're right. In principle, I mean, we will do that. But these are all equivalent definitions. But let us stick with this. Okay? It's also simpler too. Okay, so this is the equal a priori probability. Equal a priori probability. Well, I don't know. What is it called? Postulate. And now statistical mechanics, all of statistical mechanics, all of it, follows from this equal a priori probability postulate and another statement, which is the following. Define, let us call gamma of E equal to the integral of this integral I just defined. When I write dq/dp, what I mean is the integral over all the dqi's, all the dpi's. Okay, I'm not writing product of blah, 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 blah. We understand that. Let us actually, to make things clear, let's put a parenthesis. So when I write the differential this way, what I really mean is product over I, dqi, dpi. Okay? That's what I mean. All right, so now define this integral, which is the volume, essentially the phase space volume of this thick surface. And now comes Boltzmann, Mr. Boltzmann. Who tells us that the only thing we have to do in order to construct thermodynamics and statistical mechanics and everything else is to say, well, look, the entropy is equal to K Boltzmann times the logarithm of gamma of E. And nothing else. So this is the Boltzmann formula. Okay? So it's telling you essentially that the entropy is proportional to the logarithm of all the possible ways you can put the system in a microstate consistent with the macroscopic state of your system. That's what it means. Okay? Here written up with continuous distributions, but it's equivalent. So if I would have a discrete system instead of having this volume integral, I would have to, we'll do the example later on for the easing model, but I would have to take a sum over all possible discrete configurations which have more or less the same energy. Okay? So this is Boltzmann. This is what Boltzmann tells us. Now, before going on with Boltzmann, so of course when Boltzmann wrote this formula, he had to think about one thing first, which is this really an entropy? Right? Does it make sense as a definition? And what is the basic requirement the entropy should satisfy? Should be greater than equal to 0. It is greater than equal to 0, right? Because gamma it has to be extensive. Exactly. So this is one of the most important requirements. It's an extensive function. It's an extensive state function. So it's a state function, of course, and now we have to prove that it's
extensive. When he thinks about extensivity at that time, it's important. But how about today that we have those kinds of non-extensive entropies?
Non-extensive entropies. What is a non-extensive?
Like Chalice.
Oh, look. Let's not. We stick to Boltzmann, right? So Chalice, He is a nice guy, but we like Boltzmann more. Right? It's okay, but let's stick to standard statistical mechanics and standard things here. Okay, so we want to make sure that this definition is consistent with the basic requirement of extensive entropy, of having an extensive entropy, right? So how do we do that? Well, let's take a system that is divided into two parts. Let's say 1 and, sorry. So let's say 1 and 2. And, well, in volume 1 there are some particles with generalized coordinates Q1 and P1. In the other one there are some other particles, Q2 and P2 are the generalized coordinates. And momenta, the number of particles is going to be N1, V1, and E1, the energy. N2, V2, and E2 is going to be the energy of the other guy. And then what we want to do is the following. We are going to write down the Hamiltonian. The total Hamiltonian is going to be H Q1 P1 plus H Q2 P2, the sum of the two energy functions in the two parts. Now, strictly speaking, there is something I'm neglecting here, which is the energy of the eventual interaction between 1 and 2. But the point is that all this interaction is happening on a surface, right? And therefore is not extensive. So if I increase the volume of the system, this surface layer is going to be the same. And in the thermodynamic limit, this is going to scale sub-extensively and therefore is irrelevant in order to prove that the entropy is an extensive function. So I'm neglecting it from the beginning. All right, so now what I'm going to do is take the energy, which is equal to E1 plus E2, fix the energy, so fix the total energy, and compute the entropy, right? And compute entropy. Yes. Now, how do I do that? Well, when I fix the total energy, strictly speaking, what I'm saying is that E should be smaller or equal than E1 plus E2, then should be smaller or equal than E plus delta. Okay? Clear to everybody. But now the point is the following. So, if I have so if I would fix, let's say we fix the energy of volume 1, right? So if I fix the energy of volume 1, and I say this energy is between, I don't know, some E tilde 1 and E tilde 1 plus delta, then the area, the surface in the parameter space of 1, gamma E tilde 1, is going to be equal to the integral for E tilde 1 smaller or equal than H, let's call it H1, so the Hamilton function of 1, E tilde 1 plus delta dq1 dp1. Now, similarly, if I do the same for 2, I will get the same in which instead of 1, I do 2, right? I write down 2. So if I would fix one energy, I would get this surface volume. If I would fix the other energy, I would get this other volume of phase space. Clear. But now the problem is that when I fix only the sum, I'm not fixing the individual energies. I'm fixing their sum. I have many possibilities of choosing E1 and E2 in such a way as to satisfy this constraint, right? So I do not have necessarily to fix E1 and fix E2. I have many possibilities. So the problem I have in computing the entropy in terms of the volume integral of these guys here is that I have all these many possibilities to fix the global energy. Clear? So how do I sort this out? Well, I essentially do the following. If I would be fixing, so if I fix a pair, I proceed by steps. If I would be fixing a pair of E1 and E2 such that, how do you write such that? I don't remember. Such that E is equal to E1 plus E2 up to delta, okay? Then the total phase space volume of the total system, right? So gamma of E for this pair would be equal to the product of the two phase space volumes. So it would be equal to gamma E1 times gamma E2, defined as above, as here.
Sorry.
Clear?
When we have this in the phase space, this surface with energy E,
Yes.
and we give it a thickness of
Yeah.
delta. In this case, when we say that E1 plus E2 can be in the, like, in the,
Yeah, so
from E to E plus delta,
Yeah.
do we assume that the total energy can fluctuate a little bit?
yeah, the total energy can fluctuate between E and E plus 2 delta. Sorry, I wrote it wrong. So if this energy here fluctuates between E tilde 1 and E tilde 1 plus delta, and the same for 2, then the total energy will have a 2 delta.
But
Okay.
why don't we take this symmetric? Why don't we take this? I keep forgetting the word. Why don't we write E minus delta has to be smaller than E plus 1 plus E2, which has to be smaller than E plus delta?
E minus delta is to be...
This inequality is not symmetric in terms of delta. Why
No,
don't
but
we-
it doesn't really matter. It's okay. You can take it that way and repeat the proof. You
It
will
will
see
be
that
the
it
same.
will hold the same. You will see that the argument is very, very simple. It's not even a proof. I mean, it's not mathematically a proof what I'm doing. It's just a blah, blah, blah a la theoretical physicist, okay? That leads to the correct result, okay? So let's call it a proof for the sake of, okay. So we understand that if E1 and E2 would have been fixed and satisfying this condition up to a 2 delta, then the volume would have been this, right? But now we want to count the total number of possibilities, the total number of microstates that will be consistent with the macro state of having a total fixed energy. Now this is just for one possibility. Now what I have to do is count the number of possibilities, and for each possibility have this, which is the number of states, and then sum all of them. Clear? So let's do it as follows. I know that this is a point that is always confusing. Let's take now, let me make it a bit more precise. Let's do the following. Let's take, this is the line that's between 0 and E, let's say. And let us split this line into some intervals, each one of size delta, and at each point here I have an energy E, right? So roughly speaking, so within the resolution of my measurements, which is delta, the total number of, so if I want to count all the possibilities having E1 and E2 such that E1 plus E2 is equal to total E, what I can do is I select, for example, E1 equal to one of these EIs, right, in this discrete set, and then I select E2 equal to E minus EI. So this will enumerate, this construction will enumerate for me all the possibilities within the resolution of my measurements of choosing an E1 and an E2 such that E1 plus E2 is equal to E. Okay?
Yeah.
Clear? And now, for each one, for each possibility, for each, the number of states, number of microstates, is going to be proportional to gamma EI times gamma of E minus EI. This is 1 and this is 2. Okay? Because this is the volume in the total parameter space. Clear? And now, when I write down the Boltzmann entropy, what I want to write down is the total number of microstates that are consistent with the global conditions I'm giving. And the global conditions I'm giving is total energy fixed. So what is the total number of microstates? With energy E fixed. The answer is that it's going to be proportional, let's call it gamma of E, is going to be equal to the sum over I from 1 to E over delta. So these are all these points of gamma EI times gamma E minus EI. Okay? That's it. Now, I don't have just one of these guys. The reason I don't have one is that I have multiple possibilities to satisfy the constraint of having a global total energy constant. Okay? All right. By the way, this is the proof of extensivity that you find in the book of Wang. So if you don't understand my notes, which I think are more understandable than the book, but never mind, you can find it in the book itself. All right. So if this is the total number of microstates, then the entropy, the global total entropy, is going to be equal to K Boltzmann times the log of sum over I from 1 to E over delta gamma EI gamma of E minus EI. Okay? And now, these terms are not all equivalent. I mean, these terms in this sum, they're not all equivalent. They're not all the same. There is one gamma 1 times gamma 2 that is going to be larger than the others. Okay? So, select the gamma 1 and gamma 2, which is the largest. So, for example, select E bar 1 and E bar 2, for which gamma 1 E bar 1 times gamma 2 E bar 2 is largest. Now, if you select it, then you will have that gamma 1 E bar 1 times gamma 2 E bar 2 is going to be smaller or equal than gamma of E, which is going to be smaller or equal than E over delta times the log of gamma 1 e bar 1, gamma 2 e bar 2. Why? Because this is what I would get, this is the result of the sum I would get if I had only the largest term and all the others are 0. And this is the result of the sum I would get, sorry, not the log, I apologize, there's no log here. This is the result of the sum I would get if all the terms were equal to the largest. Because I have E over delta terms that are all identical and equal to gamma 1 times gamma 2. Clear? I know that it's painful, but you will get a reward at the end.
Can we repeat
Okay.
the last part?
So, here I have a sum, right? A sum of terms.
Yeah.
I'm saying pick up the largest.
Yes.
Now, it's clear that this sum is going to be greater than the largest term, because these are all is a sum of positive terms. And it's going to be smaller than the total number of terms times the largest term. Why? Because if all the terms were equal to the largest, then you would get that. So it's certainly going to be smaller than that. Okay? So it's certainly going to be, this is going to be satisfied. Okay? Now this has an important implication, because if I take the log of this, of gamma 1 times gamma 2, let me forget about writing the E bar 1 and E bar 2. This is going to be smaller or equal than the log of gamma of E, and it's smaller or equal than the log of gamma 1 times gamma 2 plus the log of E over delta. Right? But now, notice an important thing. What is the log of gamma 1 times gamma 2? Well, this is equal to the log of gamma 1 plus the log of gamma 2. This is entropy 1 plus entropy 2, right? So this is S1, and this is S2. Now, and therefore, here what we have is that essentially entropy 1 plus entropy 2 is smaller or equal than entropy of the total system, smaller or equal than S1 plus S2 plus K Boltzmann log of E over delta. But the point is that now, if you look at this, this is something, I mean, it's essentially extensive because I'm summing up two terms that correspond to two different volumes. If you imagine repeating this process for many subvolumes, it will be S1 plus S2 plus S3 plus S4, blah, 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 is going to be proportional to the volume. So this term here is proportional to the volume. Energy is an extensive quantity. This term here is proportional to the logarithm of the volume, and therefore is subleading as compared to this one. Which means that in the thermodynamic limit, when the volumes are very large, I can neglect this term as compared to this one, and I obtain that in the thermodynamic limit, I have that S is equal to S1 plus S2. And therefore it's an extensive quantity. Okay? It's not a mathematical proof, it's a blah blah blah, let's say, but it's an interesting blah blah blah, as we will see in a second. Why it is an interesting blah blah blah? I'm sure that there are some mathematicians who proved it, but we don't care. Okay? So, all right. So we esteem the work of our mathematical friends. Now we can continue with With showing why this argument is interesting in my opinion, because notice one important thing here. The way I wrote this entropy is a bit imprecise. What I should write is S of E is equal to S1 of E bar 1 plus S2 of E bar 2. What is E bar 1 and E bar 2? Are these two energies for which gamma 1 and times gamma 2 was maximum. Okay? That was my requirement. And now, let us see, what are these two energies for which E bar 1 and E bar 2, gamma, the product of these two gammas is maximum? Well, first of all, I have to have that E is equal to E1 plus E2, and I'm fixing E. E is fixed. And therefore, if I take a derivative with respect to E1 with E fixed, this is equivalent to minus a derivative with respect to E2 with E fixed. Okay? Fix E. Right? Good. Now, let us take now a variation of gamma 1 E1 times gamma 2 E2. Now this is going to be delta gamma 1 times gamma 2 plus delta gamma 2 times gamma 1, and this has to be equal to 0. Right? Because we want to find E bar 1 and E bar 2 for which this is maximal. And therefore, what we find is that delta gamma 1 over gamma 1 should be equal to minus delta gamma 2 over gamma 2. Now delta gamma 1 can be written as d gamma 1 over dE1 times delta E1. And the same thing for delta gamma 2. Delta gamma 2 can be written as d gamma 2 dE1 delta E1. Okay? Well, if I take a derivative with respect to E1 or E2, it's irrelevant because total E is fixed. So therefore, E2 is equal to...
minus sign on the...
Where?
D gamma 2?
No, it's D,
it's D.
it's D gamma 2 by dE1, not by dE2. All right? And now, I plug this in here, I get D gamma 1 over dE1 times 1 over gamma 1 delta E1 should be equal to minus d gamma 2, this is a gamma, is not an f, dE2, dE1, 1 over gamma 2, delta E1. So the delta E1 is gone. And now I can transform this integral as d gamma 2 over dE2 times 1 over gamma 2. And therefore, what I discover from these two relations is that the derivative with respect to E1 of S1, right? Because up to a k Boltzmann, this is the derivative of the log of gamma 1. So it's essentially up to a k Boltzmann is this. Should be equal to the derivative of S2 with respect to E2. This is the condition that will determine E1 bar and E2 bar. But what is the derivative of the entropy with respect to the energy? What is it in thermodynamics?
Temperature?
Is the inverse temperature. This condition tells me that E bar 1 and E bar 2 are determined by the condition that the inverse temperature T1 computed by taking a derivative of the entropy with respect to E1 should be equal to the inverse temperature E1 over T2. This is the condition of thermal equilibrium, of these two guys.
Can this thing be considered as a proof that internal energy is only a function of temperature?
No. No, because this is true always. It doesn't. That is valid only for the ideal gas. It's not. Okay? In my opinion, this is actually what convinces me the most that this definition of entropy makes a lot of sense. Okay? Makes really a lot of sense. Because it tells you that when you divide your system into two parts, then you do sum up the entropies. But for the two energies, not for arbitrary energies, but for the two energies, such that ds1 dE1 is equal to ds2 dE2, which is the condition of thermal equilibrium. Okay? Full stop. Great. So now, what do we do with this? Why this is interesting, important, etc., etc., etc. Well, so in practice, if you want to use the how's it called, the microcanonical ensemble to do calculations, then what you have to do is, of course, you have to compute this gamma of E. And then once you compute this gamma of E, then I will tell you later on, there are some tricks. You can compute this gamma of E, or you can compute something slightly different that turns out to be equivalent to the gamma of E in the thermodynamic limit. These are all details, so let's forget about that for a second. So given this, you can compute your entropy. Now, once you have your entropy, what can you do? You can compute the temperature. Or you can compute the pressure. And then you can, well, construct your differential of the entropy, blah, blah, blah. You can do whatever you want. And you can start playing the game of thermodynamics with this. Okay? So this is an efficient way to derive the thermodynamics of is not an efficient way. It's very inefficient because calculations in the microcanonical ensemble are typically a disaster. Unless you are interested in non-interacting systems, in which case they are simple. But if you have interactions, it's anyway. So nevertheless, in principle, is something that you can use in order to get information about the thermodynamics, okay, of your system. For example, you could use it to get the equation of state of the ideal gas, which is the next exercise we will do. We have half an hour, so we can do that. Now, but before deriving the equation of state of the ideal gas using this formalism, okay, now that we decided that it makes a lot of sense, I have to tell you something. So, in principle, you can let's call this section some confusion. No, some various definitions of entropy. Okay, so if you are in the thermodynamic limit, turns out that all the following definitions of the entropy are equivalent in the thermodynamic limit. In the thermodynamic limit, we have that K Boltzmann log of gamma is equal to K Boltzmann log of sigma, I will define sigma in a second, of course, K Boltzmann log of omega. So these are all equivalent definitions of the entropy for a system in the thermodynamic limit. So gamma, we already know what it is. What is sigma? Sigma is defined as the volume of, not of the hypersurface, but is actually defined as the volume of all the states in phase space is defined as the volume of all the, let me write it, okay, it's easier in this particular case. Volume of all okay, so it's the volume that is
under the surface.
is contained, that's the word, is contained by this hypersurface, okay? And if you look at the origin of energy. And omega is defined as d sigma dE. Is the derivative of sigma with respect to the energy. Because is how this volume changes as I change the energy. And it turns out that once you do this, it's clear that gamma, which is the volume of the wafer, okay, the locker, is going to be equal to omega times delta. Because delta is the thickness and omega is just the, think about doing an expansion to first order in delta, and that volume integral you will have, well, how do you prove this? Gamma is equal to sigma of E plus delta minus sigma of E, right? Is the volume of the locker. So you take the volume up to E plus delta and you subtract the volume up to E. And then you do a Taylor expansion here and you get the formula that I just wrote down. Okay? So these are all equivalent definitions of the entropy in the thermodynamic limit. Why? Because it turns out that all these quantities have the leading dependence on the number of particles that is identical and is exponential. Okay? So that is why you can trade one for the other. So it's a peculiarity of this. Now, this is quite, the fact that you have this equivalent is quite useful when you do want to do practical calculations. Now, hopefully, none of you will ever do practical calculations with the microcanonical ensemble, or the only practical calculations are, well, perhaps in the exam. Perhaps I could in the exam.
Please don't.
Who knows? That's always a possibility. Okay? So perhaps in the exam, but apart from the exam, in your research work, most probably you will not do calculations with the microcanonical ensemble. Nevertheless, this kind of arbitrariness that we have is quite useful when we do some standard calculations, for example, such as the calculation of the entropy for the ideal gas in the microcanonical ensemble. So the ideal gas is defined by the following beautiful Hamiltonian. So exercise number 1 in the exam is going to be write an H, a proper H, a proper sign for the Hamiltonian. I'm joking, hopefully.
It takes so long to write that thing.
No, if you learn it's not a big deal, right?
Still.
It's like this. No, it's like this, right? Once you learn, it's very simple. Anyway, okay. So I wonder what the public at home thinks about this digression. Anyway. Okay, so now given this, let us compute sigma. So sigma is equal to integral for all h smaller than e of dq dp. Now we have to be careful about one thing here. It is quite important. You see, in all these definitions that I gave you, this gamma was a volume in parameter space, in phase space. Now the phase space volume element has actually a dimension, right? Is the momentum times the distance. So it has momentum, the dimension of an action, right? So, and you cannot take the logarithm of something that is dimension 4, right? Doesn't make any sense. Therefore, we have to normalize this in some way. So typically, what you can do is write down this as h times 3n, right? Where h is some constant that has dimensions of an action, and this is the 3n is the total number of components that you will have. It turns out that this h has a meaning, but you cannot understand this meaning in classical mechanics. Because h, the natural normalization of these integrals is with the Planck constant. Okay? Because the Planck constant, when you think about quantum mechanics, is the elementary phase space volume. So it's natural, if you want to count a number of states, to divide the total phase space volume by the elementary phase space volume that is set by the Planck constant. Okay, I'm not pretending you to grasp immediately all of this, but I'm telling you. Okay, so when you will do quantum mechanics, and I don't know who's teaching you quantum mechanics, but asking, how can you tell us why the phase space in semi-classical, the semi-classical approximation of phase space volume is? It's essentially this, right? It's dx, dp, sorry, not smaller, but greater than h bar, right? Or h bar over 2. So it's essentially that is what makes the natural phase space volume in quantum mechanics h bar. Anyway, we have to normalize. It doesn't matter by what you normalize. Let's write h to the power 3n with the understanding that perhaps the Planck constant is the natural way to normalize this integrals. Great. Now, it's clear that my Hamiltonian does not depend on position, right? And if it does not depend on position, then I can take the integrals over the position, and this is going to be v to the power n divided by h to the power 3n times the integral for all h smaller than e of dp. So dp1, dp2, dp whatever. But now, what is this condition? Well, this condition h smaller than e is sum over I from 1 to n pi squared divided by 2m smaller or equal than e, which means that the condition is sum over I equal to 1 from 1 to n of pi squared smaller or equal than 2m times e. But now this is what? This is a radius squared in the multidimensional space in which I'm integrating, right? So if I think about this integral as an integral in multidimensional spherical coordinates or whatever, this is essentially defining, this integral here is defining the volume of a sphere of radius square root of 2m times e in how many dimensions? 3n dimensions. In 3n dimensions. Okay? That's it. Definition. Clear to everybody? So now I have to compute the volume of a sphere in 3n dimensions. So in 2 dimensions, the volume of a sphere goes like R.
Sorry?
In 2 dimensions, the volume of a sphere goes like R squared. In 3 dimensions, R cubed. And therefore, in 3n dimensions, or n dimensions, the volume of a sphere of radius r is going to be some constant Cn times r to the n. Right? So this is expected. N for us is going to be 3n, 3 big N. Now, Cn, how do you compute Cn? Well, you can compute it in many ways, but I'm not going to do it. So we are going to proceed in Wikipedia mode, and I'm going to give you the result. So the result is gamma n over 2 plus 1. Well, this is not the gamma, the volume integral before, but this is a gamma function, okay? The generalized factorial. So this is the result of for a sphere in 3n dimension. If you want to impress your friends, you can learn how to do that. I think you can find it in Wikipedia, most probably. It's written up there. We already checked. All right. So now the log of Cn, and notice one thing, that the log of Cn is going to be equal to n over 2 log of pi minus log of gamma of 1 plus n over 2. But now gamma of n plus 1 is equal to n factorial, that you know, right? And therefore you can easily imagine that log of gamma of n plus 1 is going to be approximately n log n minus n, right, for n going to infinity. And therefore the log of Cn is going to be approximately n over 2 log of pi minus n over 2 log of n over 2 plus n over 2. So this I'm writing because in a second I will take this volume and I will put it in a log, right? So what I'm going to do now is I'll go back here. I know what is the volume of a sphere in 3n dimensions of this radius. I plug in this radius here, I put it here, and I know what is Cn. And then I write down the result. Okay? So I write down that my sigma is equal to Vn h to the 3n times C3n times square root of 2m times e to the power 3n. And now what I do is I compute the entropy S, which is the log of this, K Boltzmann log of this. So I'm going to get K Boltzmann log of sigma. I'm going to get K Boltzmann times the log of C3n plus n log of V over h cubed plus 3 over 2 n log of 2m times e. Okay? So this is my entropy. And now if you plug in this expression, this one, let's see if I'm able to make a circle. Wonderful. And Giotto. So now if you take this and plug it in here, what you will get is that your entropy, your final expression for the entropy, will come out to be K Boltzmann times n. You will do the algebra at home. You promise, right? You promise. All of you promise. Great. Log of v 4 pi m times e divided by 3h squared n to the power 3/2 plus 3n over 2 k volts. This is the expression. So now what I want to do is I want to show you that this expression is correct. And the way I'm going to show you that this expression is correct is I'm going to compute the equation of state, right? From this expression, the equation of state that we all love and dream at night. So first of all, let's take an exponential. So let's take s minus this stuff here and exponentiate on both sides of this equation. So I will get exponential of s over k Boltzmann times n minus 3/2 equal to, well, the log, which is once exponentiated, gives me the argument of the log. So it's going to be v times 4/3 pi m e over h squared n 3/2. Great. So now let us take take both sides of these two equations of this equation to the 2/3. Okay. And therefore I will get exponential of 2/3 s over n k Boltzmann minus 1, and then I will have v to the 2/3, and then I will have 4/3 pi m e divided by h squared n. Okay? And now I can write down this equation as an equation for the energy as a function of the entropy, right? So energy comes out to be v to the minus 2/3, 3/4 h squared n divided by pi m exponential of 2/3 s over k Boltzmann n minus 1. Now quickly, it makes sense because, okay, now let us now take let us now compute the temperature. The temperature is dE over ds. Okay? So therefore, if I compute the temperature, you see that the only place where S appears is here. So if it's in an exponential. So if I take dE over ds, I will just take down 2/3 k divided by k Boltzmann n that multiplies everything that is written here, which is the energy itself. So this is equal to 2/3 1 over k Boltzmann times n times the energy itself. The energy, because the dependence is exponential, which by the way implies that the energy is 3/2 k Boltzmann times n times t.
Can I see the previous slide?
Previous slide where?
Previous slide.
This one?
This 2/3 that 3/2 that appeared
Which one?
on the last equation that we wrote.
This one, 3/2.
Yeah, yeah. That 3 is actually number of degrees of freedom.
Yes.
Oh, that's
Yeah, of course.
Yeah.
Yeah, we'll see. It's
Yeah.
a theorem. It's actually the equipartition theorem that has to fix this. So it's important. Yeah, you see, it works.
yeah.
When
How do
when
you pop up like this? It's crazy.
well, when it's correct, it works, right? I mean, it has to work, right? Now let's compute now the pressure. The pressure is what is minus dE over dV. Ha! But I have the 2/3 again. So I'm going to get, you see, if I take dE dV, what am I going to get? Is minus 2/3 times V to the minus 2/3 minus 1 times everything else that is all the same as before. So I'm going to get 2/3 E over V. But wait, E over V is what? Is 3/2 K Boltzmann and T. And therefore this is equal to N K Boltzmann times T divided by V. Aha! I got to the equation of state. You see? Now this teaches you something very important in life, in the life of a theoretical physicist. That when you do things, when a calculation is correct, is also beautiful. And this calculation, I think, is beautiful, right? It's really beautiful. And the fact that it comes out so nicely is really beautiful. Okay? So we give all the credit to Mr. Boltzmann, who discovered this, and next time we're going to do other stuff with the microcanonical ensemble. I'll leave you with this magic. So do it at home, because it's nice. I mean, you just see it with your own eyes. Okay?
I have this really stupid question.
What?
The equation for energy that we
Yes.
have right now, every number 3 that appears there,
Yes.
is it just a hint to degrees of freedom or
That
something?
is the number of degrees of
Yes,
freedom, right?
So if I have n degrees of freedom, they'll just be n's.
Yes, absolutely. Yes. Yeah, yeah. If you have not degrees, I said degrees of freedom per molecule.
Yeah, of course.
Actually,
Yeah.
you know, you can
Per
easily
particle.
you can easily imagine. Actually, you can easily generalize this calculation. If you want, you can do it. I mean, it's actually very simple. You can easily imagine. I leave it to you as an exercise. That let's simplify things. Let's take an Hamiltonian. Okay, I'm going to write it here at the end. Take an Hamiltonian, which is super simple, is the following: pi squared plus qi squared divided by 2. And m is equal to 1. Okay? We use the theoretical physics units. So you know what they are. Everything is equal to 1.
Pi equals to 3.
Yes. No, it's actually very important. I mean, the units I use typically are h bar equal to light, speed of light equal to K Boltzmann, equal to pi, equal to minus 2, equal to 1. Okay? So this is all equal to 1. But you cannot use the last part of these units in the exam, okay? Anyway, so try to do the calculation, the previous calculation, using this Hamiltonian and see what comes out. You will essentially
6.
get 6 instead of 3. Why? Because instead of having the volume of a sphere in 3 n dimensions, you will have a volume of a sphere in 6 n dimensions. Okay? So if you have to redo this calculation, do it for this. Okay? Actually make it slightly more complicated. Do it for this. Put an omega squared here.
Very question.
Yeah, you just have to change variables. I mean, it's not a big deal. You will get 1 over omega to the power 3n in the denominator, but it's not such a painful thing. Okay? Good. So I'll see you on Wednesday. Next week we go back to normal. Okay?
In approximately how many lectures will we start phase transitions?
I can tell you. Why are you eager to learn phase transitions?
Yes.
I see. I can tell you about roughly. Just a second. Well, we first need to do the canonical ensemble. So we will do the canonical ensemble, and then we will start easy model, and then all variety of things on the easy model, and then we will discuss phase transition. So, yeah, here it is. So we will first do the canonical ensemble.
In like 2 weeks, we'll be already doing it.
Well, for 2-3 weeks, end of October. I don't know. I mean, it depends. Yeah, we first do the canonical ensemble, then we do a lot of exercises with the canonical ensemble, a lot of practice with the canonical ensemble, because that is really important. And then after that, we'll start discussing. What? You want it?
No, thanks.
No, if you want it, I can do it. Without grades. I mean, just for you to practice.
Maybe you could give it as
Assignment.
If I give it as an assignment, it's a collective gift. I know what it is. I mean, I give it as an assignment provided all of you promise that you do it by yourself. And there is no exchange of how did I do this, how did you do that? Otherwise, I get no information, right? I mean, and you don't get any information, but that's most important. If you do it by yourself, then you get information.